Okay, now it's on. Okay, so we go to worksheets, and you go for the thermodynamics worksheet, and then you're going to go for the one that says Gibbs free energy 1. And that worksheet is going to look like this. So you're going to be working on that with your group here in just a minute. Okay, now I'll go back into here, get rid of that, and go to that worksheet that I showed you. And it looks like this. So you've got the Gibbs free energy equation. Oops, don't have the marker going. Now we do. You got the Gibbs free energy equation. And then there's a table here that you need to fill in, saying that, you know, if the enthalpy is a negative and the entropy is a positive, what will be the sign of the Gibbs free energy? And you do that for all 4 of these. Then this first question here, the condition at which the Gibbs free energy is always negative is when the enthalpy is, and it's looking for what sign it's going to be, and what sign is the entropy going to be. And then question 2, the Gibbs free energy is always going to be positive when the enthalpy has a particular sign and the entropy has a different sign. And then number 3, when the situation is indeterminate, in other words, we don't know because of a conflict with the signs, then it says low temperature is going to favor entropy or enthalpy. And what it really means when it says favor is which is more important, okay, at a low temperature, entropy or enthalpy. Because if you look at the equation, you ought to be able to figure that out. Then for these remaining questions, for question, marker, for questions 4 through 6, what you're going to do is you're going to say, you know, is the reaction going to always be spontaneous, never spontaneous, or sometimes spontaneous? So in order to do that, you're going to have to be able to say something about what you think the enthalpy is and what you think the entropy is. And then you're going to combine those together using the Gibbs free energy equation to figure out if it's going to be negative or positive. If the Gibbs free energy is negative, then it's always going to be spontaneous. And if it's positive, it's always going to be non-spontaneous. Okay? And you ought to be able to come up with that by looking at the reactions, like here. See, they're including energy in the reaction, so that's going to help you with the enthalpy. And then they've included what states things are in, and that will allow you to say something about what the entropy is. But for these 3, you're not actually doing a calculation. But then when you get to number 7, what is the value of the Gibbs free energy? If the enthalpy is a negative 32 kilojoules, and the entropy is a negative 25 kilojoules per Kelvin, and the temperature is 293 Kelvin. So that is going to give you an actual number. And then based on that number, you're going to say, is it spontaneous or not? And then there is one more page. And it's a similar kind of question. You're calculating the Gibbs free energy. They're giving you the enthalpy. They're giving you the entropy. They're giving you the temperature, so that you'll get a number here. And then depending on whether it's negative or positive, you're going to say whether it's spontaneous or not. So does that make sense to you guys? Okay, I think I got something in the chat that I didn't see. Oh, I don't see it. Okay. Anyway, so I'm going to set this up to put you guys in your groups, and you can talk to each other and guess I got to do this. Yeah, okay. Now I'll do that. Okay, one more thing here, and I'll start the groups up. Now remember, when you're in the groups, if you need to talk to me, it'll have to be in chat. Otherwise, I will not know what's going on. Okay, I think I got everybody in the right place, so I'm going to hit the button and start it. You guys can work on the worksheets, and I'll ask you, the answers to those different questions after you've had some time to work on them. Okay, so here we go. Okay, folks, we're back. Let's see. The units are going to be kilojoules, straight kilojoules. The K goes away because you multiplied it by the temperature. So you had temperature in the numerator, and then the unit was in the denominator, and so they canceled. So they're gone. Okay, does anybody have a question about this worksheet? You guys good on it? Oh, okay. I'm glad you can hear me. You can always chat. That's no problem. You don't have to have a mic working for this to go. Okay, I'm going to assume you guys are okay on that worksheet. I will post the key though, so if you want to look at it, later, it'll be there. So, okay, I'm going to shut that down, and I'm going to go get back into the lecture, the PowerPoint, and we'll be finishing this one up here pretty soon. Okay, on that worksheet that we just did, you were calculating the Gibbs free energy from the value of the enthalpy and the value of the entropy. But you can also do that in another way, and that's what we need to take a look at now. So make it a little bigger. Here we go. Oh boy, I keep messing that up. Now we can see it. So this is the Gibbs free energy of formation. And this is similar to when you did enthalpies of formation in Chem 140. And the idea is these are formation reactions, so you're forming something. And this list right here are the things that you're forming. And you're forming them from elements in their elemental form. So that's the way these things would show up. It's the way these elements would show up by themselves. So carbon would be graphite solid, oxygen would be O2 gas, hydrogen would be H2 gas, stuff like that. There's some standard conditions, but this doesn't affect things too much. But this point right here, this important, 1 mole of product. So you're going to get only 1 mole. Now that would not be an issue in some cases, but sometimes it will be. Like in forming the C3H8, and you're forming it from carbon and you're forming it from hydrogen. When you balance the equation, you end up with 1 mole. You have a coefficient of 1 on the propane, so it's okay. Or this next one down here where we're making carbon dioxide. We're making it from carbon solid and oxygen gas. And it works out that you can balance the equation and only have 1 over on the product side where the carbon dioxide is. But when we go to making the H2O, that's where it gets to be a little bit of a problem. So we're going to have H2, and then we're going to have a plus, and then we're going to have O2. We need an arrow. So I could get an arrow up there. Okay, and then we need the H2O. And I'll make these a little bit bigger so we can see them. Hopefully we can see them better. So there's our H2 gas. There's our positive. Here's our O2. There's our arrow. And then we got our H2O. Now, if we were going to balance that equation, we'd say, oh, there is a 2 oxygens here. So on the product side, I've only got 1, so I'd want to put a 2 in, right? And then as soon as I put a 2 in there, now I've got 4 hydrogens, so I'd need a 2 in front of the H2. So at that point, we'd say, oh yeah, now this is balanced. Oops, get rid of that, and get rid of this. So now it's balanced, but the problem is what we were talking about a second ago. You only want to have 1 mole of product. So this 2 here is not going to work. So that's why the formation reaction for water is going to look like this. We're going to have 1 H2, we're going to have half of an O2, and then we'll have 1 H2O. So we just got to keep in mind that that's what the reaction is going to look like. Why that's important is that in a table of these values, then this middle section is just not going to be there. They're not going to show you what a formation reaction looks like. They expect you to know these, what they're going to be. Now there is one other issue, and that is in a table of free energy of formations, it would not have anything for the hydrogen and the oxygen because they're already in their final form. You're just supposed to know that, hey, those are going to be zeros. So that what this table is really going to look like is this, where we'll have whatever is being formed and whatever is the Gibbs free energy of formation, but none of the other information that we just talked about. But does this make sense to everybody? Anybody got a question? Okay, so now we want to see what are we going to use these free energies of formation. Well, we can do something like this. So notice that where we're going to end up at in the end is a value of the Gibbs free energy for a reaction. Now we did that on that worksheet, but in that case we were using the Gibbs free energy equation, del G equals delta H minus the temperature in Kelvin times the delta S. And we had a value for delta H, and we had a value for delta S, and we knew what the temperature was, and we just put those all together, and we got our answer. But here we've got a different way of doing it. We're going to use what the E looking. Oh, these guys right here. Hang on, Victoria. I'm going to get to that because it may have been a while since you guys have seen those. Okay, we got another way of doing it. So this up here is our reaction that we're trying to figure out what the Gibbs free energy is for. Oh boy, I didn't mean for it to do that, but okay. So we've got propane, we've got oxygen, we've got carbon dioxide, and we got water on the product side. The way that we can calculate using these standard Gibbs free energies of formation is we use the Gibbs free energy of formation for the products. So that's these guys over on the right. And then we're going to use the Gibbs free energies of formation of the reactants. And of course, that's all the stuff on the left side. Then we've got the little n and the little m. And that's going to stand for the coefficients. Change the color a little bit. So in other words, it's going to go for the 3 and the 4 and the 5. And also, there's a 1 here. So that's what the little n and the little m is for. Now, what Victoria was asking about was these. That's a sigma, S-I-G-M-A, and that means you're going to sum it up. So you're going to take all of the free energies of formation for the products, and you're going to add those up. And then you're going to take all of the free energies of formation for the reactants on these guys, and we're going to add those up. So that's what we're doing in this next line here. This is the free energy of formation for carbon dioxide. It's on that table on the previous slide. This right here is the Gibbs free energy of formation for water. And I should mention that you got to be careful and make sure that you're using water in the correct form. So in this case, it's gas, because it'll be different if it's liquid or if it's solid. And then over here, the 23.4, that's the propane. I'm not going to try to draw it or spell it. And then this last here, the 0, that's for the oxygen. Remember we said that for things that are already in their elemental forms, they're always going to be 0. Now we have the coefficients to deal with. So the carbon dioxide, the coefficient is 3. So that's why we got a 3 here. Coefficient of the water is 4. That's why we got a 4 right there. Coefficient for the propane is understood to be 1. So that's why we got a 1 over here. And the coefficient for the oxygen is 5. And that's why we have a 5 over here. And then we just simplify that to get our answer. Be careful about the negative sign right there. Remember that applies to both of these. So when you're putting them together, don't forget that. Excuse me. Oh. And that's how you get your answer. So you end up with this negative value, negative 2074.2. And that is our Gibbs free energy of reaction for this particular equation. And since it is negative, it's spontaneous. That's enough letters. You know how the rest of that goes. Okay, so you guys understand how to do that, correct? Anybody got a question? We're going to do a worksheet. That's where this is going. Well, I think I got some stuff in the chat here. Let's see, is there anything I have missed? Okay, no, I'm good. We're good. Okay, so let's go to the next slide. And what this is doing is you saw these formation things before in Chem 140. Now again, it's this collaborates messing these uh, D's up. So remember that's really delta. It's not a capital D, and that's a delta. It's not a capital D, and the same thing for all of these. And then the other thing that it's doing is this right here is supposed to be a sigma right here, not a capital S. Same goes there, and the same goes down here, and also goes down there. So these equations look like what we had on the previous slide for formation. It looks like that, except you can do it with the standard formations for enthalpy and the standard formations for entropy. So going back to this slide, that's what we're doing there. I hope it's not throwing you the symbols being messed up. So we can calculate the enthalpy from the formation values. We can calculate the entropy from the formation values. And then we could take both of those and use the Gibbs free energy equation to get the delta G if we needed to do that. Now the last slide has some of the values for this. Now here's one thing to notice, and that is for the formations, the entropy formations, they're a little different because things like oxygen and solid iron and things in their elemental form, they actually do have a number as compared to Gibbs free energies that it's going to be 0, and enthalpies it's going to be 0. And then the rest of these is like what we were doing before: Gibbs free energy, carbon monoxide, carbon dioxide, water, and that last one down there is acetic acid. And we're going to do a worksheet that's going to use this kind of stuff. Let me see what this next slide is. I don't remember what we got. Oh yeah, we got to talk about this. Yeah. Okay. Something happened and Collaborate took this and for some reason it put it down here, but that's not where it's supposed to be. It's supposed to be up there. So what this is saying is the Gibbs free energy is going to be equal to the negative, and then it's got some other stuff in there. That's the gas constant, that's the temperature in Kelvin, that's natural log, and then over here that's the equilibrium constant. So, going back to a previous chapter. Okay, make it a little bigger. That is the equilibrium constant for action. Now, the thing to take away from this is this part right here. It really doesn't matter much. What we can say is that the Gibbs free energy is, well, we got it down here. The Gibbs free energy is inversely related to the equilibrium constant. So if the Gibbs free energy is negative, or in other words, making things spontaneous, the equilibrium constant is going to be a positive number, which is what it would be if we're supposed to be going to the products. So conditions that make the Gibbs free energy negative or spontaneous is also going to give the largest value for the equilibrium constant. Okay, so we're gonna go to that next worksheet, but before we do, I think maybe we ought to take a break so people can take off for a few minutes and not miss anything. So I'm just gonna, we'll get back on it at about 7:30, okay? So see you at 7:30. You're back, hopefully. So we're going to go to this next worksheet. So I'll kill this, and I need to show you where to find this stuff. So let's do that. Okay, that didn't work. Let's try it one more time. Okay, I don't see it sharing my screen, so I'll just have to tell you. Of course, the actual, oh, there we go. So again, the actual worksheet that you're needing is this Gibbs Free Energy 2. So, you go to course materials, look at worksheets, click on chapter 16, thermodynamics, and then click on Gibbs Free Energy number 2. Sorry about that. But the other thing that you're going to probably need is going to be the that last slide of the PowerPoint. So to get to that, you'll go to lecture presentations inside of course materials, and then you go down to thermodynamics, and you can click on either one of those. I just clicked on the first one, the PDF, and it'll take a little while to load. And then we're going to, I think it's the last, no, it's the next to the last slide. So for this table, because you will probably need these numbers. The worksheet assumes you're going to look them up in the textbook, and I don't want you having to go do that. So here's the numbers you're going to need in order to do that worksheet. So go ahead and open this up in Blackboard so that you've got it. So you'll need that, and you'll also need a copy of the worksheet. So and I'm going to put it up in Collaborate. So I'll stop sharing my screen, and I'll show you the worksheet for Gibbs Free Energy number 2. So it's going to look like that. Let's make it bigger again. Okay. So the first question is calculate the Gibbs Free Energy. The temperature is 25 degrees C. So you're going to have to convert that into Kelvin. Okay. Then the way you're going to solve the Gibbs free energy is first you're going to calculate the enthalpy, and then you're going to calculate the entropy. So you're going to use those two equations using formation values like I was talking about a moment ago. And then you put those into the Gibbs free energy equation. And then decide based on the result of the Gibbs free energy, is this reaction going to be spontaneous at this temperature? Here is the reaction that you are doing it for. Then for question number 2, although this one's going to take a while to do, obviously. And then for question number 2, you're going to find the Gibbs free energy, except this time you're going to use the enthalpies of, the Gibbs free energies of formation for the products and the reactants. So you're going to use that equation that I showed you guys just a second ago. The free energies for the products, then you subtract from that the free energies for the reactants. Now, the number ought to be the same for 2 and 3, okay? Ought to be getting the same value. And then question 3 is considerably more difficult. And so I want to talk about that after we've done these other two. Get you guys set up to get into your groups, and I'll be clicking the button here in just a second to do that. And then you guys can work in groups. I'll give you, like on this first one, this is going to take a little while. So I'll give you guys like 10 minutes to do that because it'll probably take you 10 minutes to solve number 1. And then I'll ask a group for their answer. Okay? So I am going to push the button here. Make sure everybody's in their group. Yeah, looking good. Okay, so I think I got everybody in their groups. So I'll hit the start. Hi, folks. Okay, you ought to be back in the same room again now. And I'm going to mute a couple mics here. I missed some of that. Okay, I don't get it, but whatever. Anyway, okay, so we're done with this chapter unless somebody has a question. So is there a question on this chapter? Okay. Yeah, I know we're moving along like a two-legged turtle or something. Anyhow, it's a little slower doing it this way, isn't it? Okay, let's go to chapter 17 then. Oh, that's big. So we're going to go to chapter 17. This is electrochemistry, and we did a lab on Monday that was electrochemistry, so we're a little bit behind with the lecture, but not too bad. So anyway, electrochemistry input for a lot of stuff, a lot of technology, because electrochemistry is what's in battery technology. You know, wouldn't have the Tesla, wouldn't have battery powered, which is pretty important. Wouldn't have cell phones, although all these cell phones in this picture are totally out of date. But anyway, you still get the idea that an enabling technology for modern technology is, for modern devices, is batteries. And so also, electrochemistry shows up in biology, believe it or not, cell potential, or let's see, action potentials in muscles, the nerve potentials, um, and then it's also applicable in things like medical devices, implantable medical devices. Batteries are important. So anyway, we're gonna get into that now. So to do that, we sort of need to go back and look at some oxidation reduction concepts. So this is actually from Chem 140. We have an oxidation reduction reaction. Everything's happening in one container. It's all happening in this test tube over here. So we have a solution of silver nitrate. We have a piece of copper. We put it into the solution. This is like the lab that we did 2 weeks ago. And come back later, the solution is now green, and our copper wire now has a coating of silver on the outside. So we could represent that reaction uh, with what we see here. And we've got the copper labeled as a reducing agent, silver nitrate as an oxidizing agent. Well, let's see how we get to that. So I'm going to erase and put that in here. Oops, what has happened here? Oh, no, it's okay. Sorry, guys. I thought the recording had stopped. Anyway, see how I can do on this. We can break this apart into two half reactions. So on one side, I've got the copper solid, and then that's going to then, I need an arrow. And then that's going to produce copper 2 plus cation. And then we're also going to get 2 electrons. So copper solid then is losing 2 electrons, and it's now becoming part of a ionic compound, the copper nitrate that has the green color. I'm not including the nitrate because it is around and is not participating in the reaction. Okay, so we can take the process I just put up here, and we're going to label that as an oxidation, and that means that you are losing electrons. Then I know you guys realize I'm not supposed to have a capital U on the CU over here. Okay, now we're going to do the same thing with the silver. So we've got a silver cation, so that's Ag, and then it's going to be plus. And then we're going to add to that 1 electron. And then we need another arrow. Oh, you can't see anything I am drawing. That's not good. I would say you could look at the recording, but that's no fun. Oh, wow. Is this not working for, is anybody seeing what I'm drawing? Let's put it like that. Okay, so some people, no, Erica can't. I'm getting like a half and half situation here. Okay, I can, I don't know what's going on here. Well, I'll go ahead and I'll put it in for the people that can see it. I am going to have to suggest that you other guys take a look at the recording later, and then I'll try to talk through it also to make it clear to everybody. So, got to do a little work on my picture here, or what I'm drawing in. So what I'm doing is I've got a silver cation, so that's Ag plus, and I'm combining that with a single electron, and then that is going to produce silver solid, Ag, and then, you know, I really hate some parts of collaborate. This is really bad. Okay, And then I'm going to type in one more phrase here, and then I'll talk through it for the benefit of the people that can't see this. Okay, so here's what I've done. I took looking at the reaction at the bottom of the page, I took the copper solid, the CUS, and I wrote that down. Then I have an arrow. Then after that, I have part of the copper nitrate compound that you see over on the right. I just have the copper cation part. So I've got Cu2 plus. And then I'm adding to that, then I have 2E negative. So that's for 2 electrons. So what has happened there is the copper solid has lost 2 electrons. It's become Cu2 plus. That's an oxidation. It has lost electrons. Then what I wrote below that was I took the silver from the silver nitrate. The nitrate isn't really important because you see you have nitrate on both sides of that arrow. So it's really a spectator in this whole process. So we can leave it out for what we're doing to better understand it. So I've just got the Ag plus, and then I have a single electron. So I have E negative to represent that single electron. Then I have an arrow, and then I have Ag solid, Ag of S in parentheses. So that's the silver that we're putting on the top of our copper wire. Well, that process is a reduction. Reductions are gaining electrons. And there is let's see, there's a way to remember this. It's called ORIG. Oxidation is losing, OIL, and reduction is gaining. So that's the rig. Anyway, somebody told me that. I guess it's okay. I don't know. It's kind of stupid, but anyway. Now the thing is, the 2 electrons that we got when the copper oxidized and lost 2 electrons, those are the same electrons that we're going to be adding to the Ag plus from the silver nitrate. The problem is we don't have the same number of electrons. So we would have to take our second reaction, our Ag plus 1 electron, making 1 Ag solid, and we would have to then multiply that by 2 in order to get the same number of electrons. So we would have to multiply it by 2. Now we have 2 electrons that we're producing and 2 electrons that we're using. Okay? So you guys may want to take a run at this of taking a reaction and breaking it apart into the 2 half reactions. Now the other part of this slide that I want to zoom in on is the reducing agent and the oxidizing agent. The way to think about this is something cannot lose electrons unless those electrons have some place to go. Okay? So that's why the Ag plus in the silver nitrate is the oxidizing agent. That's the place for the electrons to go from the copper. Likewise, you cannot have something then gaining electrons unless there is a place for them to come from. So for the Ag plus to be reduced, it has to get electrons from the copper. So that makes the copper the reducing agent. So what you need to be able to do when you have one of these one of these oxidation reduction reactions or redox reactions is be able to see what is the oxidation, what is the reduction, what is the reducing agent, and what is the oxidizing agent. Okay? Now I'm going to try to see if I can fix our issue where I'm having been able to see me drawing on the slide. So what I'm going to do is I'm going to kill the slides and I'm going to bring them back in again. That might fix it. So let's try that. I'm drawing on the first slide. Okay, so my question is, can anyone not see that I wrote on the first slide, can you see? Wow, I guess I fixed it. Okay. So now, let's go a little bit further on this thing. I'll go to my next slide here. So you can see that for these different oxidation reduction or redox reactions, we're going to need a way to be able to see what is the oxidation, what is the reduction, so that we can then figure out what is the oxidizing agent and what is the reducing agent. And a way to do that is with oxidation numbers. You did this in Chem 140, especially if you had me for the class. And this is all based on a number line, like we see here, -3, -2, -1, 0, +1, +2, +3. If the oxidation numbers go from right to left, like we're seeing here, then that means that it's a reduction. On the other hand, if it goes from left to right, it's an oxidation. It doesn't matter if you're going only, say, from +1 to 0. That's still a reduction. Okay? Now, I got it in words here also. A reduction, the oxidation number becomes negative or less positive. An oxidation, the oxidation number becomes positive or less negative. And then we've got an example of a reaction below that where we've got magnesium becoming part of magnesium chloride. And then we've got hydrogen in hydrochloric acid becoming hydrogen gas. So below that are the oxidation numbers for magnesium, for the hydrogen in the hydrochloric acid, for the magnesium in the magnesium chloride, and the hydrogen in the hydrogen gas. And we're going to have some rules on the next slide for doing this, but for right now, let's just say it works like this. If something is in its elemental form in the way that we normally find it, then its oxidation number is going to be 0. So that's why the magnesium solid is 0, and that's why the H2 is 0. Because that's the way you normally find magnesium is a solid metal, and hydrogen is a diatomic gas. Then, if something is in an ionic compound and it has a charge, then its oxidation number is the same as that charge. So the hydrogen in the hydrochloric acid, it's going to have a 1+ charge, so it's going to make its oxidation number +1. And the magnesium, it's going to be Mg2+, so therefore its oxidation number is going to be +2. And for the chlorides in both the hydrochloric acid and the magnesium chloride, that's going to be -1 because its charge is 1 negative. Then we just follow to see what happens to the oxidation numbers as we go from the reactants to the products. So changing color here. When I go from 0 to +2, tell you what, I'm going to erase and do that again. When I go from 0 to +2, if I look up here on my number line, I'm going from 0 to +2. It makes that an oxidation. Now going to the blue marker. When I go from +1 to 0, I'm going to the left on my number line. I'm going from +1 to 0, and that makes it's a reduction for the hydrogen. So we know that for the hydrogen, it's a reduction. And for the magnesium, it's going to be an oxidation. So do you guys see how you use numbers or oxidation numbers in order to do this? Anybody got a question on that part? So now it's just a matter of figuring out what are the oxidation numbers. So I'm going to go to this next slide. And here are the rules for oxidation numbers. Some of this stuff's not as important as some of the rest of it. So we're going to focus in on what is, really important. First thing is elements that are in their elemental form, their oxidation number is always going to be 0. Oxidation number of a single atom ion, Na plus, Cl negative, stuff like that, is the same as its charge. Oxygen is going to be -2 in a compound unless it's a peroxide, and then it's going to be -1. So for oxygen, possible oxidation numbers are going to be a 0 if it is elemental form, if it's O2. Otherwise, it's going to be -2 or -1, although you will have to know that it's a peroxide to know that. You should be able to get it from the formula. We're going to have a worksheet. I think that'll help on this. Now, hydrogen, it's going to be a -1 if it's bonded to a metal. So that would be something like sodium hydride, NaH. For something like NaH, where the hydrogen is bonded to the sodium, its oxidation number then is -1. If it's bonded to a nonmetal, like what we just did a second ago with hydrochloric acid, HCl, then its oxidation number is going to be +1. Now, these rules under this, the fluorine and the halogens and all that stuff, we don't care. That's not going to matter. Then the last 2 points that we have to focus on. The sum of all the oxidation numbers in a neutral compound is going to be 0. Okay? The sum of the oxidation numbers in a polyatomic ion is going to be the same as the charge of the polyatomic ion. Okay? So I think what I'm going to do here is put the worksheet up on the screen, and then I'm just going to ask people for some answers, and we'll see how that goes instead of doing the groups and all that stuff. Okay? So I'm going to break out of this, and I'm going to go to the oxidation numbers worksheet. And that is this thing. Oh, by the way, on the second, guys, I took the 2 worksheets that you guys just did on the Gibbs free energy, and the keys are now available in Blackboard. That was what I was doing right then. Okay, let's make this bigger, 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 and bigger. Okay, there we go. And now I think what I want to do is I'm just going to go down the list, or not go down the list, I said that wrong. I'm going to go into my attendance app, and I'm just going to let it randomly pick people, and I'm going to ask you what you think the oxidation number is, and we'll see how that works out. So, Diana, what's the oxidation number for the chlorine in Cl2? I'll make this even bigger so we can definitely see it. You can text it. Oh, Victoria, I'm sorry about your computer. Okay. Uh, oh, yes, Lily, what's up? I see you've got your hand up.
How do I make it bigger? I can't see anything.
Oh, seriously? Because I'm making it bigger from here. It's not making it bigger at your place?
No.
Oh, that's
Something happened. I got logged out of Collaborate and then I had to sign back in the past like minute and a half, and then now it's all tiny and I don't know what I did.
okay. All you other guys, is it bigger for you? Is it not bigger for anybody? Okay. I'm going to try. Oh, by the way, Diane just said that the oxidation number for chlorine and Cl2 is 0. Thank you. Okay, I'll tell you what, I'm going to kill this and then bring it back and see if that helps. Okay, there seems to be something like that that happens. Um, okay, Lily, is it bigger now or is it still small?
It's still tiny, like really tiny.
Okay, then I'll tell you what. Um, Go to Blackboard.
Okay.
Go to. Oh, that. Okay. How do you zoom in on it, Victoria? Can you tell us? Oh, I just thought of something. Do you guys have like on the left side a icon? Okay, left side. Do you have one icon below the other icons? Well,
Oh, that thing that says show view controls, that funny thing?
uh,
Oh, I get
okay,
it. Okay.
okay. So you can. Okay, and like Delani said. Okay, okay, yeah.
There
So you
we
can either
go.
use. Okay, okay. So we're all good. That's good.
Woohoo.
Yeah, we're all right here. Okay, so we know now that the chlorine in Cl2 is 0. So now let's do this next one. I know you guys can't hardly see it. It's actually Cl negative. I'll ask someone for the answer. Erica, what's the oxidation number for Cl negative? I guess I better make sure Erica's still here. Yep, she's still here. Erica. This is so weird to do this way. Okay, I have a feeling she has stepped away, so I'm going to. Oh, we got 0 for the first one because it is CO2, so that is the elemental form of chlorine it's a diatomic gas, Cl2. I'm going to go to somebody else for now. Uh, yeah. Victoria, what do you think the oxidation number is going to be for chloride, Cl negative? Hey, she says -1. Anybody disagree there? Nope, it's the same as the charge. So now we got the next one. So we've got Na solid, and we need to know what its oxidation number is. Emsada, what do you think it is, please? She says 0. Any disagree there? Nope. Okay, so our next one is Na plus. Shaniqua, what do you think it is? I say that and she leaves. Oh, okay. Well, I'll go to the next person. How about Jamie? What do you think it is for Na plus? +1. Anybody disagree? Anybody got a question? Okay, now we're to O2. So I think the person I'm getting ready to call on, nope, not there. Okay. How about Stephen? What you think for O2? 0, he says. Anybody disagree? Nope. And I'll do the next one. I disagree. Well, what do you think it is then? -2. It's going to be -2 if it's in a compound, unless the compound is a peroxide. But when it's in its elemental form, the way that we would normally find oxygen, like the oxygen we're breathing right now, that is a diatomic O2 gas, and therefore it's in its elemental form, and so its oxidation number is going to be 0. Yep. Hey, don't say sorry. I I appreciate participation. Never say sorry. Anyway, N2. So N2, just like O2, is in its elemental form, so its oxidation number is going to be 0. Now we're to the aluminum cation, Al3 plus. Lily, what do you think the oxidation number is going to be for Al3 plus?
I think it's +3, the same as its charge.
That would be correct.
Woohoo!
Okay, now we've got a compound that's got 2 kinds of atoms, hydrogens and oxygens. We've got to determine what is the oxidation number for one of the hydrogens and for one of the oxygens. But when we put them together, they should add up to 0. So we're going to take whatever it is for hydrogen and multiply it by 2. And we're going to add that to whatever it is for oxygen, and it should add up to 0 because it is a neutral compound. So that, what do you think the hydrogen is? She's going to go with 2, +2. But if it's +2 and I multiply that by 2, I'm going to have +4. Is that going to be good? No. So let's do this. What's the oxygen going to be in this compound? Victoria and I just had a big discussion about it. Ah, yes. There we go. So the oxygen is going to be -2. So back to SADAP. What do you think the hydrogen has to be then for this to work out? No, because we want it to add up to 0 when we're done. So what would hydrogen have to be? And then multiply it by 2 to balance out -2. See, we want to balance out the -2 with a +2, but we've got 2 hydrogen atoms, so what would each one of them have to be? Hey, okay, thank you. So if the hydrogen is +1 and there's 2 of them, that adds up to +2. That's going to balance the -2. Everybody got it? Yeah, that's right. Each one is going to be +1. Okay, we're going to do the same thing now with this next compound, and that is NO2. I think, if I can read. No, it's NO3. Okay. Is it NO3? Let me make this bigger. Yeah, it is. Oh, it's NO3. Can't tell if there's something on my screen or is there a negative. I believe there's a negative. So it's NO3 negative. So this is going to be a little more complicated because when we're done, we should end up with a -1 after we combine all these together. So I'm going to call on somebody and we'll see what we get. Delaney, what do you think the oxygen is going to be in this polyatomic ion? but this is not peroxide. It's for the oxygen, just one oxygen. We said before that oxygen is either going to be 0 or something if it's in a compound or with another atom, unless it's a peroxide. If it's peroxide, it's going to be -1. Ah, okay, it's going to be 2. It's going to be -2. And there's 3 of those. So 3 times 3 times -2 is going to be equal to -6. I want to end up at -1. There's only one nitrogen there. What would the nitrogen have to be so as to end up at -1? I'll ask someone else for that one. How about Jamie? What do you think? What would the nitrogen have to be? +5. So you guys see what we're doing here. If we combine -6 and +5, we end up at -1, and that's what our charge is. So the nitrogen has to be +5. What we're going to be noticing is certain elements, like nitrogen, can have almost any charge. They just take on whatever charge is necessary to make everything balance out. You got friends like that, right? You know, they'll act however they have to fit in. Anyway, bad joke. Okay, let's look at another one here. Another person. Come on, phone. There we go. Erica, what do you think the oxygen is in NO2? It's a compound, neutral compound. Better make sure she's here. Yep, she's here. Erica. Okay, I'll wait. I have no idea what's going on, folks. I sort of think she's leaving and coming back. And I'm still waiting on Erica to tell me what the oxygen's going to be. Tell you what, I'm going to go to someone else. Imsada, what do you think the oxygen's going to be in the NO2? She says -2, which is correct. Oxygen is always going to be either 0 if it's in O2 like we had up here. So up here, it's going to be 0 because that's the elemental form. Or we're going to see that oxygen is going to keep on being -2, -2, -2, unless it is a peroxide, in which case then it's going to be -1. Okay, so now we need a value for the nitrogen. So this is going to follow the same thing we did for the NO3 negative. So Sadap, what do you think the nitrogen is going to have to be in order to balance out 2 oxygens, each oxygen being a -2? +2, but we've got two of them. So 2 times -2 is -4. Ah, I don't know why it's doing that for. I'm trying to erase some things. Ah, ah, +1. Well, if we make nitrogen +1, well, okay, let me do the math over here if I can get this thing to stop moving around. Okay. Anyway, hey, that's it. +4. Yeah. If the oh God. Okay, if the nitrogen is +4, then that's going to balance. Oh yeah. Okay. See, once you get this, these things seem really pretty easy, really, because again, you got 2 times -2 for the oxygens is going to be -4. So the nitrogen has to be +4 to balance that out. Now, this next one's going to be a little more challenging. In fact, it's probably the most challenging one here. And that is this dichromate anion. It's Cr2O7 with 2 negative charges. So when you're at the end, you have to have 2 negative charges remaining. So why don't you guys try to figure out then, well, let's do this much. Somebody, Shaniqua, are you here? Let's see. Nope, she's not here. Okay, let's ask someone else. Diana, what do you think the oxygen is going to be in the C2072 negative? Just one of them. Not all of them together, just one of them. Yeah, -2. So -2, and then you already did the math. 7 times -2 is going to be -14. So now we have to figure out then what the chromium is going to be. Notice that there's 2 chromiums and also that we have to end up with the charge being 2 negative. So think about it for a second of what the chromium would have to be. And I'll ask somebody. Okay, so Stephen, what do you think the chromium is going to be? He says 7. Okay, let's put it in here. So if the chromium is +7 and there's 2 of them, then 2 times +7 is going to be +14, right? So put that over here. And that would be what we'd want to see happen if this was a neutral compound. But this has 2 negative charges. So we need to end up at a -2, right? So instead, we really want to here have plus um, +12, not +14. So we want it to be +2, because if we do that, we're going to end up then with the 2 negatives that we need to match up with our charge up here. So to do that, what would we want the charge on the chromium to be? I'm having trouble getting rid of that. Let's see, here we go. Yeah, plus 6. Now I can get rid of the 7, and I'm going to make that plus 6. Now this is probably the hardest one up here. Has anybody got a question about doing this one? You're almost always going to be safe with making your oxygens negative 2s, unless it's, O2. Uh, and then you just have to work everything else out to make that fit. So if we're trying to end up at 0, or we're trying to end up with a charge. Okay? So now, I tell you what, I have a feeling you guys are getting a little exhausted at this point. So I think what we'll do is we'll call it good at number 11, and we'll pick back up on these on Monday. So does anybody have a question about anything, though, before you all take off? Okay, I'm not seeing any questions, so I think we're good. So anyway, you guys be safe as best you can till I see you on Monday, okay? So you all take care. If you need anything, contact me, email or text or whatever you need to do. Okay? So have a good evening. Oh, you got a question about test 3. Yeah, what's up? Oh, wait a minute. You didn't ask me, though. Or you did it. Okay, hang on. Oh, I got a question. Another question. Oh, yeah, Delana, you're asking, are we going to have an exam 4? My answer is I don't know yet, but I'll give you some warning before we get, if we do have one, it's going to be really towards the end. Okay? And the question was, are we going to have a final? Yes, we're going to have a final. It's in May. It's on the list of assignments.
Dr. G?
Yeah, hang on.
Yeah, it's me. It's me. Okay.
Hi. Yeah, so I don't want to put this screen away because I need to make a record of how far we went on the sheet here. But
Oh,
yeah, you're going to send me your screenshots, right?
yes.
Okay. Yeah, send those to me. I remember us talking about this when you took the exam, and it was showing it, and so yeah, I don't understand what happened. It's really weird.
Okay.
But but yeah, send me the screenshots, and then I have a note here somewhere, and I'm just not finding it right off the bat. But as soon as I do, I can, I can respond to you better.
Okay, sounds good. I'll do it.
Okay. So
Okay.
okay, you take care now. Be careful.
Yeah, it's you. Bye-bye.
Okay. Bye bye.